I have a pleasure to introduce our next speaker, Professor Pavel Etingof from Massachusetts Institute of Technology. The title of the talk is Twisted Traces and Positive Forms on Quantized Kleinian Singularities of Type A.
Okay, thank you. So let me share my screen. Just a second. Okay, can everybody see my screen?
Yes, we see your screen.
Okay, thank you very much. So I will talk about twisted traces and positive form for quantized Kleinian singularities of type A. And this is contained in the paper. It's published already, but the archive number is here. And it's joined with Daniel Kluyev, Eric Rains, and Douglas Stryker. So first I want to recall the algebras that are involved, which are quantized Kleinian singularities of type A, or also called generalized Weil algebras. And they were actually introduced by Vladimir Bavula, who I think is in the audience. Happy to see him here. He introduced them in early 90s, more than 30 years ago. And let me give the definition. So suppose I will work over the complex numbers, and suppose that P is a monic polynomial of degree n over the complex numbers. Then I define the algebra A, which is A sub P, but I will drop the subscript from now on. It has three generators, U, V, and Z. And the defining relations are like here. Commutator of Z with U is minus U. Commutator Z with V is V. So this means that Z is a kind of weighting element, and the weight of U is -1, weight of V is 1. And then the product of V times U is equal to P of Z minus 1/2, and U times V is equal to P of Z plus 1/2. So this implies that the commutator of U and V is P of Z plus 1/2 minus P of Z minus 1/2. And so this algebra carries an increasing filtration, which is defined by assigning degrees to generators. So the degree of U and degree of V is n, and degree of Z is 2. Then you can see that this commutator relation, commutator of U with V, is a polynomial of degree n minus 1. And because of this, left-hand side of this identity is higher degree than right-hand side. So this means that associated graded algebra is going to be commutative. So associated graded algebra is generated by still U, V, and Z, but the defining relation now is that U times V equals to Z to the n. We just take the leading terms of all relations. This, therefore, it's an algebra of regular functions on the Kleinian surface, Xn, which is Kleinian singularity of type n, an minus 1. And this surface is defined in the three-dimensional space by the equation U times V equals to Z to the n. And moreover, because we started with a non-commutative algebra, took associated graded, and obtained a commutative algebra, this commutative algebra, GR A, is going to have a Poisson bracket induced by the non-commutative product on A. And this bracket will be of degree -2. And it's given by the following formulas. Poisson bracket of Z with U is -U. Poisson bracket of Z with V is V. And Poisson bracket of U with V is n times Z to the n minus 1. So the last relation is obtained if you look at the commutator relation here. The leading term of polynomial P of Z plus 1/2 minus P of Z minus 1/2 is n times Z n minus 1. And that's exactly why we get this relation. And this A, therefore, is what people call filtered quantization of this commutative algebra A, straight A with a Poisson bracket. And also, this Kleinian singularity, that's a classical construction, can be obtained by taking a quotient of the plane by the action of cyclic group Z mod n. So namely, at the level of functions, we can take polynomials and two variables and consider action of Z mod n on them in the following way, that P is multiplied by a root of unity of degree n, and Q is multiplied by the inverse root of unity. And then we can look at the invariants. So the invariants are going to be P to the n, which we call U, Q to the n, which we call V, and P times Q, which we call Z. And they then satisfy this equation. U times V equals to Z to the n. And the Poisson bracket, well, we have a standard Poisson bracket on PQ, the canonical bracket, which is P Poisson bracket with Q equals to 1. But actually, it's convenient to renormalize it and say that it's 1 over n. And then the Poisson bracket on U, V, and Z will be exactly as above. So therefore, we can say geometrically that Xn is the quotient of the two-dimensional plane, C2, modulo this action of the cyclic group. And this is true not only as algebraic surfaces, but also as Poisson surfaces. So it's compatible to the Poisson bracket. Now, so the algebra A depends on initially n parameters, which are coefficients of the polynomial P, but actually it only depends on n minus 1 parameters, because we can always shift Z to make this polynomial free of the subleading term. So we can make it to have the form Z to the n plus A1, Z to the n minus 2, plus so on, plus An. And then A2 through An will be the parameters of this algebra. So in particular, we can consider the following examples. So the first example is n equals 1. So in this case, well, we can assume that our polynomial is P of Z equal to Z. And then this is just the usual Weil algebra generated by U and V, where commutator of U and V equals to 1. We don't need Z because Z is actually the product U times V. Z plus 1/2 is the product U times. Now, if n equals 2, then we have a one-parameter family. So again, we can make a polynomial free of the linear term. So P of Z equals to Z squared minus C. And then the algebra we get is enveloping algebra of the Lie algebra SL2, modulo the relation that the Casimir element, which is the central element of this algebra, equals to C. So where Casimir element is this for the standard generators E, and F, and H for SL2. Now, in general, we have this algebra besides the filtration. It also has a Z grading, which is compatible with the filtration. This is a filtration by it's introduced by the grading is introduced by the element Z. So the degree of an element A is the eigenvalue by which Z acts on A. And so A0 therefore is just polynomials of Z, and AK for every non-zero K is either U to the minus K C of Z when K is negative, or V to the K C of Z when K is positive. And we can view this grading as an action of C star. So element T of C star acts on A by T to the K times A, where A has degree K. Okay, so this is background. And now I will go to the main topic, which is twisted traces. So this is defined initially in large generalities. So suppose I have an arbitrary associative algebra, not necessarily commutative. And suppose I have an automorphism, which I call G. Then there is a notion of a G-twisted trace. So an ordinary trace has the property that trace AB equals to trace BA. So that's what I would call a trace. But a G-twisted trace is a generalization. It's a linear function T from A to C, such that for every two elements A and B, T of AB is equal to T of B times G of A. So if G equals to 1, this is the usual notion of tracing. And so the space of such traces, which I will denote by Tg of A, can be interpreted as the Hochschild homology, zeros Hochschild homology of A with coefficients in the bimodule AG dual. So AG here is a bimodule, which as a vector space looks like A, and left action is also the usual left multiplication, but right action is right multiplication twisted by the action of G. So this means that, let's say, x, y acting on A is going to be x times A times G of y. And then I also recall what is zeros Hochschild homology of A with coefficients in M, where M is a bimodule. It is just the quotient of M by commutator of A with M. So now I want to assume, in addition, that this algebra A, script A, is filtered by positive integers, and the element G preserves the filtration. And then we will say that a twisted trace T is non-degenerate if the bilinear form A with B equals to trace AB is non-degenerate when restricted to each filtered piece. So then we can take the associated graded, GR A. So the pieces, graded pieces AI are Fi plus 1 of A modulo Fi of A. And then if T is non-degenerate, then the orthogonal complement of Fia in Fi plus 1A is canonically identified with this AI, with the quotient. And so therefore we obtain a linear isomorphism from straight A to script A, where phi is a direct, so this is just direct sum of those phi i's, and the associated graded of this phi and associated graded of this phi is the identity. And this map is called the quantization map attached to this non-degenerate twisted trace T. So if A is commutative, then phi of A can be denoted by A hat. So if I were a physicist, I would be denoting it by A hat. And speaking the language of quantum physics, this is the quantum observable attached to the classical observable A. Certainly, phi cannot be a homomorphism because A script is non-commutative and A straight is commutative. So there is a quantum anomaly, but that's how quantum mechanics goes. And so the next thing I want to define is short star products. So these traces give rise to certain explicit products on this straight A algebra, which are non-commutative and identified with the curly A, and which are called short star products. So for this, let me take A to be a commutative Z plus graded algebra with A0 equals to C. And by the way, this is not the same grading as we had the Z grading by eigenvalues of the element Z. In fact, in that case, the graded algebra, which is defined by xy equals to Z to the M, it's actually bigraded. It has a degree with respect to Poisson bracket of Z, and also it has degree of polynomial. So it's graded by Z squared in this case. And this is the other grading. So we take Z plus graded commutative algebra, and then a star product on this algebra is an associative product, which has the following form. It starts with the usual product, but then there are correction terms. And these terms are homogeneous of degree minus I. So Ci of AB are homogeneous of degree minus I. So therefore, if you have an element of degree n called A and an element of degree m called B, then Ci of AB equals to 0 for I bigger than n plus m. Just for degree reasons, because Ci of AB would have degree less than 0, and there is no non-zero elements of degree less than 0 in our algebra. Now, the proposition here is that if I consider, well, I can introduce, because I have a linear isomorphism between straight A and curly A, I can introduce a new multiplication on straight A by adopting it from curly A. This means that A star B is just phi inverse of phi of A times phi of B. So I'm going to multiply my classical observables by taking the corresponding quantum observables and multiplying them in the non-commutative quantized algebra. And then the theorem is that the Ci of AB becomes 0 actually earlier than it should. A priori, it should become 0 when I is bigger than n plus m. But here it will become 0 when I is bigger than twice the minimum of mn. So if m is less than n, it will become 0 above 2m before we reach m plus n. And so this is a remarkable property of this star product. And star products with this property are going to be called short, because the sum is shorter than it should be. And now, if you are given a star product on A, you can define a bilinear form. And the bilinear form, I am assuming that my algebra is commutative with zeroth term being just the ground field. And so therefore, I can take for two elements A and B, the constant term of AB, which is just Cm plus n of A comma B, which is just a number, where A and B are of degrees m and n. And now note that if star is short, then this is going to vanish unless m equals to n. And therefore, this means that shortness condition means that the pieces of the grading are orthogonal with respect to this product. So that's why this is a good definition. And then we say that this star product is non-degenerate if this bilinear form is non-degenerate. And when the star product is short, the pieces are orthogonal, so this is equivalent to it being non-degenerate on every AI. And the theorem here is that the above star product, which is attached to a non-degenerate twisted trace, is non-degenerate. And conversely, every non-degenerate short star product is of this form. So therefore, we have a bijection between, so if you fix the algebra straight A, then we have a bijection between triples on one hand, curly A, filtered quantization of A, G, an automorphism preserving filtration, and T not equal to 0, non-degenerate twisted trace, modular scaling of these traces, and non-degenerate short, well, actually, I don't need to say that T is not 0, because if you want to be non-degenerate, it's a non-degenerate twisted trace, and then non-degenerate short star products on A. And we can describe how to go back. So given star, we can take the filtered algebra, straight A, equipped with this new multiplication star, and the associated graded will be the old algebra. And then we can take a unique filtered linear map G from A to A, such that constant term of A star B is equal to constant term of B G of A. and this exists because of non-degeneracy and is unique. And it turns out remarkably that this G is an algebra automorphism. And then the T is just the constant term map. So this way we can go back and forth in this diagram. And maybe I should mention that the notion of a short star product appeared in physics literature in the work on three-dimensional superconformal field theory. And so this study was motivated by that. Now, what I want to talk about is how to compute these traces. That's important in the physics applications and also in representation theory. So let's go back to Kleinian singularities. So in that case, I have this algebra script A, which has a Z grading. So it has an action of C star given by this formula. And now I can take an element from this C star corresponding to a number T. And I want to compute these GT twisted traces and see which ones are non-degenerate. So let me take the polynomial P in the factorized form. P of x is the product from j equal 1 to n, x minus alpha j, of course, without loss of generality, because we have fundamental theorem of algebra, any polynomial factors. And I'm going to, so now it will become somewhat analytic because the formulas for the trace will involve integrals. So I want to first assume that the real part of alpha j is between -1/2 and 1/2. It's in the general case can be obtained by analytic continuation. And then what I define is the trigonometrization of P. So this is going to be the polynomial boldface P. And then simply every root alpha j is replaced by minus e to the 2 pi I alpha j. So that's the polynomial of the variable capital X. And the main theorem is the following. The space of GT twisted traces is n-dimensional if T is different from 1, and n-1 dimensional if T is equal to 1. And such traces are given by the following formula. So first, let me explain that by definition of the trace, it vanishes. It's a homogeneous function, so it vanishes on AK when K is different from 0. And therefore, it only needs to be computed on A0. A0 is polynomials in one variable Z. So this is a functional on polynomials in one variable. And good examples of such functionals are integrals of these polynomials against a certain measure or weight function, as they say. And indeed, this trace is given by this following formula, integral over the imaginary line, r of x times w of x dx, where w of x is this function, e to the 2 pi I cx, g of e to the 2 pi x over p of e to the 2 pi x, where p is the boldface p I defined, and g is an arbitrary polynomial of degree less or equal to n-1, so that would be n parameters, if t is not equal to 1. If t is equal to 1, it has to satisfy the condition g of 0 equals to 0, so here is your n-1 parameter. And c is just log t, basically. So c is the number with real part between 0 and 1, such that e to the 2 pi I c is t. So that's an analytic formula. And now if what happens if your roots go out of range and cross these lines, real part of alpha is plus minus 1/2, what happens is that the expression under integration, it has some poles, and these poles are going to hit your integration contour. And the contour will have to retreat to avoid those poles and become curved. But then you can return it back to the straight position, but then you will pick up residues. And so the formula will be the integral plus a bunch of residues. Now, also for generic alpha j's, this trace is non-degenerate. So it defines a system of orthogonal polynomials, pk of z, which are just phi of z to the k. And these polynomials are determined by the condition that they are orthogonal with respect to this weight function. And because the star product is short, the star product of z with z to the k is going to be z to the k minus 1 plus bk zk plus ak zk minus 1. And this results in the classical three-term relation for these orthogonal polynomials. X times pk of x is equal to pk plus 1 of x plus bk pk of x plus ak pk minus 1 of x. So for example, when n equals 1, p of x equal x, and capital P of bold P of x is x plus 1, then the trace exists only when c is different from 0, and it's, in that case, unique up to scaling. And the weight function is this, e to the 2 pi I c minus 1/2 x divided by 2 cosine hyperbolic of pi x. It's convenient to switch to the real variable y, which is ix, and then the weight function takes this form. E to the 2 pi c minus 1/2 y divided by 2 cosine hyperbolic of pi y. So this function dies at infinity very fast and exponentially decaying, and therefore integral of this against any polynomial converges. And these pk of minus iy are the classical orthogonal polynomials, which are called the Meixner-Polacek polynomials. And another example is n equals 2 when p of x is x squared plus beta squared. And then this boldface p is x plus e to the 2 pi beta, x plus e to the minus 2 pi beta. And the traces here form a one-dimensional space for c equals 0 and two-dimensional for c dot different from 0. And the weight function is as written here. And also there are limiting cases when alpha goes to plus minus infinity. And for c equals 0, we must have alpha equals to plus infinity. So the weight function is going to be like that. And this is what's called the continuous Hahn polynomials. So this arises when you can have a representation theory of SL2. Look at U of SL2. Sorry, not U of SL2. Modular a central character. And take the invariant star product. And these are special cases of hypergeometric orthogonal polynomials where these parameters ak, bk, and ck can be computed explicitly by product formulas. But in general, they are only semi-classical orthogonal polynomials. So it means that we don't have explicit product formulas, but only have some, still it's better than nothing. You have some complicated recursions defining ak and bk, which are similar to, which are variants of discrete Painlevé equations. So here is an example. I'm not going to discuss it for the function w of y is 1 over cosine cubed of pi y. And the last thing I want to say is about positivity. So if your parameters are real, you can define a Hermitian version of the inner products. Just take the bar of the first or the second argument. And then you may ask when this inner product is positive definite. And that question is relevant to physics because physicists like to take completion of A with respect to this inner product and make a Hilbert space, which will be the space of states of your quantum mechanical system. And so, for example, if n equals 3 and p of x is x cubed plus beta squared x, and g equals 1, so in this case, turns out to be only one positive trace up to scaling, even though there may one parameter family of traces, but only one of them is positive, and the weight function is w of y is equal to 1 over cos pi y minus beta, cos pi y plus beta. And for example, in beta equal to 0, you get this thing. But the curious thing here is that this trace is not algebraic. That's maybe the most curious thing in my talk. If we normalize it by t of 1 equal to 1, t of z is going to be 0, but t of z squared is going to be the ratio of these two integrals, which comes out to be 2 over pi squared minus a quarter. So you see, you cannot renormalize this to make it a rational or algebraic number. It's a transcendental number. And that's really curious and interesting feature of this theory. Okay, thank you very much. Дякую, слава Україні.
Thank you. Thank you for a great talk.